I'll change it when I post it up. Okay, so this is one of the funny things about math. This is so outdated that it doesn't get out of our textbooks, and I don't know why. So the idea is that you don't have any graphing tool in front of you, and you have to know what the graph is. 50 years ago, 100 years ago, that was a problem. They didn't have, even when I was in college, graphing calculators just came out. I was like the only one that had a graphing calculator. The TI was not really in business. Casio was making the graphing calculators at a different time. And when I was in undergrad, my junior year, they came up with Maple, Mathematica. Mathematica was the first one. It was computer algebra systems where you can plot anything you want. Just put it in there, just like Desmos. And now today you have Desmos and Mathway at your fingertips. So this is really outdated. But the purpose in your textbook is that you don't have any clue what this graph looks like, and you can't plot points because you might miss something. So it's not like it's not a line. So you might miss something out there. So how do you find all the important points, plot those points, know the shape of the graph, and then draw the curve? That's the purpose that's in your book. But we have the tools. So we're going to go backwards. We're going to draw the graph and look at the graph first, get all the answers, and then go through the analysis and see how they match up. Okay? So the first step is, if you were asked to graph x to the fourth minus 32x plus 4, what would you do? If I said right now, graph this, what would you do? Put it on your calculator. Pull open your laptop, right? Use Desmos. Then it easily will plot it for you. So graph the function. And this is what it looks like. I've messed with it a little bit so you can see what I put in there. And I also went, and Desmos is really cool. You can go there and just click the point that you want to see, and it pops up the coordinates of the point. So this point right here is the nadir, or the nadir, the minimum, just like on the BMI graph. So this is an interesting point for us. So I clicked it so I could see what it was. So identify any flat point or any interesting point by going and clicking on them so you know where they are. That point is a minimum. We call this point a critical point. Right? There's more than this than you can get from a critical point. In the next example, I'll show you. You can get more than this, but this is the only one. If you look at it, what's interesting about this? Only that bottom point. Everything else is like just a curve. The next step is to draw arrows on your curve so that you can identify where it's decreasing and increasing. So I just went and did that, and I wrote it in words. It's decreasing before x equals 2. It's increasing after x equals 2. So far, so good? This should seem like really piece of cake now. And then we draw something called a slope chart. If it's decreasing, what should the sign of the slope be? Negative. If it's increasing, what should the sign of the slope be? I'm glad I taught something in here. So what we do is, this is called a slope chart. I should have put y prime right here. Here it's negative because I knew it was going down because I can see it on the graph. And here it's positive because it's going up. So I know what the sign of the derivative should be in these two regions. Good so far? This should seem like a piece of cake from everything we've done. Bella? So I copied the previous so you can see it. And I just wrote down here where the plus and the minus came from in case that's dropped off when you're going through this step by step. The plus and the minus represent the signs of the derivative. Now, the next step is to determine the regions of concavity. This is new, right? We say when it's a curve that it's a bucket that holds water, we call that concave up. If it's a bucket that doesn't hold water, we call that concave down. Right? So concave up curves look like this, concave down curves look like this, and sometimes curves could be pieces attached one to the other where it's concave up, then concave down, then concave up again. Could be wiggly, like a sign, right? That goes up and down. So so what's the region of concavity here? What this curve? Always concave up. I can see it. It's always concave up. And we draw what's called a concavity chart. Whenever the graph is concave up, the second derivative, that's the derivative of the derivative, is positive. Whenever the graph is concave down, the second derivative is negative. It's kind of the slope of the slope. And I don't want to go through the theory of why that's true. We're going to accept it for now and just move forward. So it's always concave up. So the second derivative is always positive, and the shape is always like this. So this is called the concavity chart. And this time I was good. I put that this is f double prime that I'm looking at. That's the derivative of the derivative. So far making sense? Domingo? Anybody have questions so far?
Why are we looking at the derivative of the derivative?
So you can actually piece it together. The derivative of the derivative is the slope of the derivative function. And you'll notice if you have wherever the slope is increasing and decreasing, if it's increasing and decreasing, then the second derivative will be positive. So it'll be a concave down shape. You can almost see that anyways from the first derivative alone. The first derivative is really where you get all that information anyways. This just refines it. So the idea is that the person that's really doing this from scratch has no idea what the graph is looking like. So it would be the same, you're recreating those 1950s era when you say no calculators allowed and no computers allowed. And I'm going to give you a test. Now we're back in the 1950s. The point, this one didn't change concavity, but the place where it changes concavity is called an inflection point. And that is like a wicked important point in biology. My biology students used to call it a life-changing moment. Something changes. Where we used to see inflection points are things like if a plant is growing and the seasons change. The plant might be growing at one, accelerating a different way, and then accelerating. Once it's cold and gray, it's accelerating differently. And you can see it. You can actually see the concavity changing. So it could be increasing and then the concavity changes. It's really cool. In regular math class, we kind of dismiss it, but it's actually really important. Okay, so now here's the stuff they want you to do in the book. They want you to pretend. It's really hard to pretend, but just pretend you didn't see the graph and you don't know anything about it. You don't know that it looks like this, and you don't know that there's a minimum at 2 and minus 44. You don't know any of that. You're supposed to discover this on your own.
I thought you had x to the fourth, so now you have x squared.
Oh, I think it becomes x to the fourth in a second. Yeah, I think I corrected. There it is. All right. So the first step to find those flat points, the place it's flat is where the derivative is 0, right? Because it's decreasing would mean that it's going down, negative. Increasing means going up. 0 would mean neither. It's not going up or down. It's completely flat. So to find a flat point, you take the derivative first, power rule, and then you take the derivative and set it equal to 0, and you solve for x. And all of the stuff you ever did with polynomials is to lead you right up to this point. So you can do this. This is just to find the flat point. We call that a critical point. That's the only important point we had on that boring graph. So here's how you do it. You factor out the 4, x cubed minus 8 equals 0. That's difference of squares. Because if I let my a be x and my b be 2, this is really x cubed plus 2 cubed. And this is the difference of cubes formula, just so you can know what I'm doing. So I factored it out. In reality, I never get anything I can factor. I don't even bother. I just go to my solve key on my computer and just tell it to do it. Everything we do that's real, you won't be able to do this. Everything that's fake, you'll be able to do this because it's doctored up. It's a cooked problem. So I copied whatever you had on the previous screen. That's the copy of it. And you can see the only place where this is 0 is at x equals 2. But you knew that. Did you know that already? You knew that because you cheated and you looked at the graph, so you already knew that. That happens at x equals 2. Even my Georgia Tech students had trouble with this. You have to get the y value because it's an x and y value that defines a point. Right? A point in the plane is defined by 2 coordinates. That's the x and y. How do you get the y value? You take the x value and you plug it back into the y function. So students from Georgia Tech would often take the x value and plug it back into the derivative. And what would they get if they did that? 0, because that's how we found it in the first place, right? You set the derivative equal to 0. So they get 2, 0 as their coordinates. And then it would be a big mess. So the critical point is 2 minus 44. We don't know it's a minimum yet because we haven't seen the graph. So far, so good?
You find the y value and plug it into the original function.
Right. Correct. What would happen if you took the y value, plugged it into the derivative? What should you get? Yeah, right.
I just wanted to make sure.
Yeah, it's really important that you know y too. Because you're trying to draw the original graph. You're not trying to draw the derivative. And that's why the points that what you're doing is, when you were little, you used to make a plot by taking x and y's and plotting the points. You can't do that here because the graph may be complicated. You won't be able to see things. So what you're trying to find is just the important points and then connect the dots between those. That's what you're doing. Now you make the slope chart. We already know what this looks like too, right? But here's how you do it. You take a point before that critical point, which is x equals 2. A point before it, 0 is always easy to plug into formulas. You take a point after. I usually take something really huge because I can see the sign. All I need is the sign of the derivative. I don't need the number. This was the derivative. I have it over the top so I don't forget it. When I plugged x equals 0 in there, I get negative 32, and it's negative. So the slope is negative before x equals 2. If I plug in something huge, like 10,000, I don't need to put it on my calculator. 10,000 cubed, big number? Is it? Is it going to blow away 32? Yeah, so whatever is positive. That's all I need to know. So it's a huge positive number, so I'm not going to go further. I just need the signs. I don't need the values, unless it's super easy for me to see the values. And there's my slope chart. Before x equals 2, the sign of the derivative was negative. After x equals 2, the sign of the derivative. Now I know what the shape of the graph looks like. But you already knew that because you already looked up decimals. Do you see how outdated this is? Outdated. I went to West Point on Friday, and they have old books from, like, they call it handbook of this, handbook, and they actually, that's what they did. They didn't have, you know, they had to walk to school uphill both ways in the cold and graph using derivatives. Okay, now to make the concavity chart, you find the second derivative. Maybe I'll make a little tutorial video if you want to see why this works. It's pretty neat. But you find the second derivative. Y prime, I know, it's 4x cubed minus 32. How do you find the second derivative? Do it again. Y double prime is 12x squared, so it's easy to find. Then you find the zeros, or the roots, of the y double prime. There's only one. It's x equals 0. See that? If I plug in x equals 0 to 12x squared, I get 0. And then you check the signs before and after, like you did in step 8 or 9, whenever you did it for the derivative. So you do the same thing you did for y prime, you do it again for y double prime. So I just chose big, huge numbers to the left of 0 and to the right of 0. Can you tell me what's going to happen before I click to the next slide? They're both positive because when you square something, it's always positive, right? So if you go way out to the left, I get positive. Way out to the right, I get positive. Those numbers are chosen to be before and after 0. Positive because x squared makes it positive, and positive again. And so now I'm ready to draw my concavity chart. That's what it looks like. Positive before, positive after. What does that tell me? It's always concave up. It's never going to change concavity. So another thing that Georgia Tech students used to do is they used to just find the 0 and tell you that it was a change of concavity. They'd say, oh, there's my inflection point. They're going through a procedure, running it through a mill. So they didn't take that extra step. Now you use all that analytical data to sketch the curve. You did this before in pre-calculus with roots. I know you did. So the only two pieces of information that were important that you were after were the slope chart and the values of the important points. That's like 2 minus 44. So you take those slope charts down and you graph it. This was the important point. There it goes. Before it was decreasing, after it was increasing. As if I'd never seen it on decimals. Andy?
Why did you choose 0 then?
Because I had to go through the motions here because I don't know what the graph looks like. So there could be a change in concavity at that anywhere where there's a 0 and the second. Yeah, I have to do that. Right? You don't know what it looks like, then it might do this, right? It can't already. I know because the first derivative says it goes like this. But you have to go through that work to see that. And on the test, there were some issues. I only graded one sections, but they didn't label their graphs, so I don't know if they know where the minimum's supposed to be. You have to actually like put numbers on it. I'll give you the blank these things, and you can put it. Notice that I put it dropping by 10s here and dropping by 2s there. You can choose that so it looks decent. It doesn't have to be what you saw on decimals. Okay, any questions?